Quantities and chemical reactions. Quantitative analysis measures the quantity of a substance. It could be as a mass or a concentration of a solute. The limiting reagent is the reactant that is completely consumed in a chemical reaction. So it's all used up, the reaction stops because it can't go further without more of this reagent being added. Excess reagent, the reactant that there is more of than is needed. So usually we try to have like 10% extra at least of our excess reagent, just to make sure that our limiting reagent gets used up. Okay, so let's say you're going to have a bake sale. You're going to bake some cupcakes. The recipe on the box calls for the box of cake mix, 300 milliliters of water or milk, 75 milliliters of oil, and 3 eggs. This will make 24 cupcakes. So you have the following: 10 boxes of cake mix, 2 cartons of eggs, so that's 24 eggs, 4 liters of milk, 1 liter of vegetable oil. So what is your limiting reagent? So if I have 10 boxes, what am I going to run out of first? So 300 milliliters of water or milk. That's per box, so 3 boxes I would need 3,000 milliliters or 3 liters. And I have 4 liters, so I've got more than enough milk. It's in excess. 75 milliliters of oil, so that's per box, so 10 boxes would need 750 milliliters, which is less than 1 liter, so that is also in excess. 3 eggs per box, so I would need 10 times 3, I would need 30 eggs, but we only have 24, so this is our limiting reagent. We're going to run out of eggs first. So the number of eggs limits how many cupcakes we can make. What is the maximum amount of cupcakes you can make? The maximum yield. It's not 240 because I can't make 10 boxes unless I go to the store. But we're going to pretend that the store is broken. It's closed. It's not there. So, 24 eggs. How many boxes of cupcakes can I make if I have 24 eggs? So 24, the recipe calls for 3 eggs each, so 24 divided by 3 is 8 boxes. I can make 8 boxes of cupcakes, or 8 times 124. So I can make 192 cupcakes, considering nothing else goes wrong. So eggs limit how many cupcakes we can make, and we can make 192 cupcakes, which is a lot of cupcakes. Okay, limiting reagents limit the amount of product you can yield, but they can also be used to control a reaction. Examples of this are winemaking. If your parents make any wine or liqueur at home from fruit, you'll know that the sugar, or they'll know that the sugar limits the alcohol content. And it can be used in baking too, like your texture of baked goods. If you have too much or too little of baking powder or baking soda, it can really change your texture. Quantities of limiting reagents must be carefully calculated and measured in these situations. How do you determine the amount of excess reagent required? Well, sometimes it's trial and error. If you're trying to precipitate out a solid, it might be that you keep adding drops of another liquid till it stops precipitating out. That's very time consuming. You can run samples against a standard curve. A standard curve is when you plot data from known concentrations, and then you run your sample against the curve, and you compare it to the curve. And they do that for blood and urine analysis. but it is always a good idea to have 10% extra for your excess reagent. So let's say you need 20 moles of something. In order to have excess, you would have 10% extra. 10% of 20 is 2, so 22 moles is 10% extra. You could take your value and just multiply it by 1.10, and that will calculate what you need plus the 10%. So determining which reactant is the limiting reagent. Sometimes we're given the quantities of reactants. We need to figure out the mass of product possible. So you've got to figure out which one is the limiting reagent, because this will limit the amount of product produced. Now, dimensional analysis can really help us here. We can use dimensional analysis to determine the limiting reagent and the theoretical yield in the same calculations. But you have to start with a balanced chemical equation. So again, we've got molar masses, we've got mole ratios. So we can figure out how to use our ratios, our units, to figure out the math. You have to do this in two steps though, because you need both reactants. You can figure out how much mass you can produce from each reactant and then compare them. The smallest mass is the theoretical yield. So the smallest mass of product is the theoretical yield, because the limiting reagent has run out. We call that, even though it's a smaller amount, we call it the maximum quantity of product that can be produced. So we're going to do this reaction. Aluminum reacts with copper 2 chloride. If 0.25 grams of aluminum react with 0.51 grams of copper 2 chloride, who is the limiting reagent? And most likely you will also be asked, what is the theoretical yield? Okay, so we're looking for, we've got two products here. One's a solution, one is a solid. 99% of the time, you're going for the solid, so we want to figure out the grams of that. The molar mass of copper is 63.55 grams for every 1 mole. So we're setting up our useful ratios. Aluminum, 26.98 grams per 1 mole. And then copper 2 chloride, 134.45 grams per 1 mole. All right. So we want to figure out the mass of copper. So what are the units for mass? They're grams. So we want G of copper, grams of copper. Where do we find that? We see this in our molar mass. So we're going to start with the molar mass. So we're going to start with aluminum. Okay, so 63.55 grams of copper we want on top, because we want to finish with grams of copper, over 1 mole of copper. All right, so now we need to go between copper and aluminum. So to do that, the only way you can go from one entity to another is with your mole ratios. To get the mole ratio, we need a balanced chemical equation. So we forgot to do that. So we will need 3 copper 2 chlorides to balance the chlorine in the aluminum chloride. So we need 2 aluminum chlorides, so we need 2 aluminums and 3 coppers. All right, so we need to get rid of whatever's on the bottom of our ratios. So we need to get rid of moles of copper. So we use our mole ratio. We need 3 moles of copper for every 2 moles of aluminum. And we're just using aluminum because we have to do it for both reactants. So it comes first in the reaction, so I did it first. So we've got aluminum. So moles of copper, but not the numbers. Cancel. Now we've got moles of aluminum on the bottom. We need to get rid of those, so we need another ratio or value that has moles of aluminum. And we've got it right there in the molar mass. We've used this, can't use it again. Okay, so now 1 mole and 26.98 grams of aluminum. So now moles of aluminum cancel, but not the numbers. Now we've got 26.98 grams on the bottom. We need to get rid of that. So now we can use our last value for aluminum, which is the mass. So now grams of aluminum cancels. The only unit left is grams of copper. There's no formulas you need to follow. You're just literally using what is on the bottom has to be on the top. So you're using mole ratios and any other ratio that you're given, like molar mass or Avogadro's number. So now 63.55 times 3 times 1 times 0.25 divided by 2 divided by 26.98. Any number that's on the top you multiply, any number that's on the bottom you divide by. So this is equal to 0.88329 grams of copper, and we can only have, this mass has 2 sig figs, our molar masses had 4. We're doing multiplication and division, so we can only have 2 sig figs in our masses. So we can make 0.88 grams of copper if all of our aluminum got used up. So now we're going to repeat it for copper 2 chloride. We still want grams of copper. So now we multiply by the mole ratio, but this time it's copper. We've got moles of copper, so moles of copper go on top. And we need to get to copper 2 chloride because that's the reagent we're interested in. So now put in the numbers. So moles of copper cancels, but not the numbers. Now we need to get rid of copper 2 chloride. So what has, we should have crossed that out. What has moles of CuCl2 in it? Well, the molar mass. So 1 mole copper 2 chloride and 134.45 grams. So now moles of CuCl2 cancel, but not the numbers. Now I'm going to multiply it by the grams of CuCl2 so that those units cancel. So now do the math. 63.55 times 3 times 1 times 0.51 divided by 1 divided by 3 divided by 134.45. And you will get 0.24106 grams of copper, which is 0.24 grams. When you round it off to 2 sig figs. So, which one of these two numbers is the smallest? So it is this one. 0.24 grams of copper is the smallest amount we can make. So once its reagent that it comes from is used up. We can't make any more. If we have more, we can make more. So you come back here, in whichever reagent you made it from, that is your limiting reagent. So copper 2 chloride gets used up before aluminum does. If aluminum was limiting, we would have to use a lot more copper 2 chloride to make all of the aluminum get used up. So you look for the smallest amount of product. That's your theoretical yield. And then the reactant that it came from is your limiting reagent. And that's how you do these questions.